Trigonometry, Chapter 4, Graphs of the Circular Functions, Section 3, Graphs of the Tangent and Cotangent Functions. Video 1, Constructing the Graph of the Tangent Function. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous sections, we constructed the graphs of sine and cosine. We observe the following. Both have periods of 2 pi, and hence quarter periods of pi over 2. Both have y equals 0 as the midline. Both have amplitude of 1 above and below the midline. The quarter period behavior of sine starting at x equals 0 is middle, high, middle, low, middle. And the quarter period behavior of cosine starting at x equals 0 is high, middle, low, middle, high. We also determine how to change the period and amplitude and invoke translations. For f of x equals d plus a times sine of the quantity b times the quantity x plus or minus c. The period is 2 pi over b, the original period divided by b. The amplitude is the absolute value of a. The vertical translation is d, positive is up, negative is down. And the horizontal translation is c, plus is to the left, minus is to the right. In this video, we construct the graph of f of x equals tangent of x. We will do this by analyzing the unit circle. But first, we need to disambiguate our use of variables, meaning we need to make sure they're not ambiguous. When we developed the graph of f of x equals sine of x in a previous video, we extracted information from the unit circle. We carefully constructed points of the form arc length, comma, second coordinate. That's because the arc length was the input of the function, so the x needed to represent the arc length, and the output was the sine of the function, which on the unit circle is the value of the second coordinate at a point on the unit circle. We did this because we used the variable x as the input for the function, and hence had to not refer to the first coordinate on the unit circle as x. I should say as x there. We continue this usage of variables, letting x be the input of the function f of x equals tangent of x, and referring to the coordinates of the point on the unit circle as first coordinate, comma, second coordinate. At its core, the first coordinate in an ordered pair is called the abscissa, and the second coordinate is called the ordinate, but this usage is not common. Recall that for an arc S, highlighted in blue, on the unit circle, tangent of S equals the second coordinate over the first coordinate. For example, for this arc of length pi over 3, the tangent is the second coordinate over the first coordinate, square root of 3 over 2 over 1/2, which simplifies to the square root of 3. We will analyze what happens to the tangent at points around the unit circle. Let's start with a blank coordinate plane. Here we have our unit circle for reference. Notice tangent of x is undefined when the first coordinate is 0 in the unit circle. Remember, we're using x as the input of the function, not as the first coordinate of the point on the unit circle. So x is an arc length. Now, tangent is undefined when the first coordinate is 0 because tangent is second coordinate over first coordinate. This occurs when the first coordinate is at an odd multiple of pi over 2. So 90 degrees times 1 or times 3, 5, 6, 7, 9, odd numbers of pi over 2s, or in reverse. This will create vertical asymptotes at these values on our graph. So at x equals pi over 2, we have a vertical asymptote because tangent is undefined at pi over 2. And at 3 pi over 2, 3/4 of the way around the circle. And for negative values of x, the arc goes clockwise, giving asymptotes at negative pi over 2. And a negative 3/4 around the circle is negative 3 pi over 2. Of course, this continues indefinitely in both directions. Now, notice that tangent of x is equal to 0 whenever the second coordinate is 0 in the unit circle. Again, x is referring to the arc length, not the first coordinate of the points. So, when the second coordinate is 0, tangent is equal to 0. This happens at multiples of pi, whole number of semicircles. These become x-intercepts. So at 0, or at pi, or even at 2 pi, we're going backwards at negative pi, or at negative 2 pi. Now, let's look for some other nice points. Starting at pi over 4. The coordinates are equal at pi over 4, and so tangent is equal to 1. So we can put this point here. The point pi over 4 comma 1. Remember, for these points, the x-coordinate of this point is the arc length, and the y-coordinate is the tangent of that arc length. Now, the same thing happens at 5 pi over 4, where the x and the first and second coordinates are equal, creating the point 5 pi over 4 comma 1 on the graph. Negatively, this also occurs at negative 3 pi over 4 and negative 7 pi over 4. Not sure why I didn't illustrate those. At arcs coterminal to 3 pi over 4 and 7 pi over 4, tangent equals negative 1 because the first and second coordinates are opposites. So negative 5 pi over 4, negative pi over 4, 3 pi over 4, 7 pi over 4, all the arcs that terminate at the highlighted points on the unit circle. Between consecutive asymptotes, and I seem to be missing a couple of asymptotes here, each branch is increasing. So we connect the dots and it looks like that. And here's a cleaner version without the unit circle. Nice and smooth. Now, what's the period? You would think it's 2 pi because that's one trip around the unit circle. However, notice the distance between consecutive asymptotes is pi. For example, 3 pi over 2 minus pi over 2 is 2 pi over 2, which is pi. And also, between pairs of consecutive asymptotes, the branches are identical. This means the period of tangent is just pi, unlike sine and cosine, whose period is 2 pi. So changing period there, period of tangent is pi. The quarter period is pi over 4. Let's analyze the quarter period behavior over one cycle. We'll use the cycle negative pi over 2 to pi over 2 because that's the one that contains x equals 0. At x equals negative pi over 2, we have a vertical asymptote. Remember, the quarter period is pi over 4. At x equals negative pi over 4, we have the point negative pi over 4 comma negative 1. At x equals 0, we have an x-intercept, a midline point, if you will. At x equals pi over 4, we have the point pi over 4 comma 1. And at x equals pi over 2, we have a vertical asymptote. So, between pairs of vertical asymptotes, consecutive pairs of vertical asymptotes, the quarter period behavior is vertical asymptote, negative 1, 0, 1, vertical asymptote. This particular cycle starts at x equals negative pi over 2. Here's a summary of the graph. Period is pi, distance between consecutive asymptotes. Asymptotes are at odd multiples of pi over 2, 1 pi over 2, 3 pi over 2, 5 pi over 2, and then negatives. X-intercepts are at multiples of pi, 1 pi, 2 pi, 3 pi, 0 pi, etc. Branches are increasing, so they're going up as we move from left to right. And the quarter period behavior is vertical asymptote, negative 1, 0, 1, vertical asymptote. This one is starting at negative pi over 2. Now you try. Pause the video and try the following 4 questions to answer about the tangent function. Here's your fair warning if you haven't stopped the video yet. Solutions in 3, 2, and 1. My advice is to remember the locations of the two asymptotes, two consecutive asymptotes, and negative 1, 0, 1 going across quarter periods.